Welcome viewers to the NPTEL lecture series on the calculus of variations. This is the 12th lecture of the series. Recall that in the last lecture we had considered functions of several independent variables. So, there we considered this functional I of z, which is double integral over certain domain D in R2 x y plane, and here on this the surface z is defined here. So, this is z as a function of x y, and here this functional was considered I of z as function of x y independent variables and z as function of x y, and then z x of x y and z y of x y d x d y. So, here we had seen that the necessary condition is the following equation, that is f z minus del x of f z x minus del y of f z y equal to 0. So, here we had considered in the last lecture the example that I of z as double integral over d z x square plus z y square d x d y and z equal to some g x y on delta d, that is this is delta d, the boundary of domain D. So, here this case f is, which is a function of x, y, z, z x, z y. In this case it is z x square plus z y square, and so here f z is 0 and f z x is 2 z x, f z y is 2 z y, and so we get minus del x of 2 z x minus del y of 2 z y equal to 0. So, this let us say this is 12.1, earlier it was something. So, let us give it 12.1 number, and so here this 12.1 implies this condition, and so this gives us minus 2 z x x minus 2 z y y equal to 0. So, multiplying by minus we get, and dividing by 2 we get z x x plus z y y equal to 0, or this is Laplacian of 2 dimension, Laplacian of this equal to 0, where this Laplace operator in 2 dimension is del x x plus, so u plus del y y of u. So, and so we get thus z must satisfy the Dirichlet problem that is Laplacian of this 2 dimensional z equal to 0 in D and z equal to g x y on the boundary of D. So, what it says that the solutions of this Dirichlet problem optimize the functional I z. Therefore, the extremals of I z are the solutions of this 12.2, the Dirichlet problem. Here in the next example, so if we consider here this example, let us give this name here, this example. (12.2). Of course, we considered this earlier also. So, example 12.3. Here we consider I z as double integral over d of z x square plus z y square plus z some function f x y here and dx dy and z equal to g x y on delta d. So, here this 12.1, that is f z minus del x f z x minus del y f z y equal to 0 implies that f. So, f z derivative here f is for this f here, which is z x square plus z y square plus z f x y gives f x y, because f z gives you this small f and then minus del x of 2 z x minus del y of 2 z y equal to 0. Simplifying this, we get z x x plus z y y equal to 1 by 2 f x y. Thus, hence z must satisfy the Poisson equation that, namely that two dimensional Laplacian here of z equal to 0 in d and half of. So, this that is z x x plus z y y equal to 1 by 2 f, which is function of x y in d, and z x y equal to g x y on delta d. So, this is the generalization of the Dirichlet problem, that is the Poisson equation. Here the right hand side is non-zero. So, it is a non-homogeneous problem. Thus, therefore, the extremals of I z must, these are the solutions of the Poisson equation. This is 12.4. The solutions of the Poisson equation 12.4. Now, we consider here the example which we had mentioned in first few lectures, that surface area of this is given by square root of 1 plus z x square plus z y square d x d y. Just recall that here we know that surface area of S is given by. So, here the situation is like this, and here this domain D, on this we have this surface S here, and so this element area d s, and this is n cap here, and so this is over S, this d s is surface element, surface area element, and this we have seen that this can be written as over S absolute value of n cap d s, which is, if we use the parameters u and v, we know that now. So, here any point P here is given. So, P has the coordinates. So, position vector of P, let us say R is the position vector of P, that is then x I plus y j plus z as a function of x y k here. So, the here point P has the coordinates x, y and z as a function of x y, like this. And so, here the parameters are x and y, and therefore, this will be equal to, now it will be projected onto this. So, projection is D, projection of S on x y plane, that is d u v plane here is now x y plane, and so the projection of the surface is D here, and so we get this n, absolute value of this n d s. d s is positive, so it comes out of the absolute value. Now, here we know that this n is r x cross r y, and this is r x is I plus z x k cross product j plus z y k, and so you can see that this comes out to be minus z x I minus z y j plus k. And so, this A of S, area of S, which is double integral over d now of this absolute value of n, now dx dy, this should be ds is now dx dy. And so, you get this absolute value of n as square root 1 plus z x square plus z y square and dx dy. So, that is what we had obtained earlier also, and so in this case we have. So, thus now for the functional, here this area of now S can be. So, here we have I of z, which is integration over d square root of 1 plus z x square plus z y square dx dy. And so, here f is f of x y z x z zx zy, in this case is square root 1 plus zx square plus zy square. And so, this 12.1, which is, that is f z minus del x f z x minus del y f z y equal to 0, implies that minus del by del x of this thing 1 over. So, here you will have 2 will cancel. So, z x over square root 1 plus z x square plus z y square. So, you will have 1 by 2 root that, and then twice of z x. So, that 2 will cancel here, minus del over del y of z y over root 1 plus z x square plus z y square equal to 0. So, we can multiply by minus, or del by del x of z x over root 1 plus z x square plus z y square minus del by del y of z y over root 1 plus z x square plus z y square equal to 0. So, that is the equation we get, which can be simplified like this. So, here we will have, so using that u upon v derivative formula. So, you get z x x square root 1 plus z x square plus z y square minus z x into z x x plus z y z x y over square root 1 plus z x square plus z y square over 1 plus z x square plus z y square. That is the first term, plus z y y 1 plus z x square plus z y square minus z y into z x y plus z y to z y y over z y square upon 1 plus z x square plus z y square. This is equal to 0. Simplifying this, we get the above equation. We get z x x to 1 plus z x square plus z y square minus z x square z x x minus zx zy zxy plus zyy 1 plus zx square plus zy square minus zx zy zxy minus zy square zyy upon. So, that this term can be taken on the right hand side. So, we get this equal to 0, and we can see that this zxx zy square will. So, here this thing we can cancel here, this zx square zxx will cancel with this, and similarly this zyy will cancel with this, and so we are left with zxx into 1 plus zy square minus these two terms will give us twice zx zy zxy plus zyy into 1 plus zx square. So, that is what we get finally. Z has to satisfy this necessary condition. Now, going to higher order functionals. Now, let us consider 3 independent variables. So, I u, now u is a function of x y z. So, we have now let us say triple integral over certain volume V f of x y z. Now, these are free independent variables, and u is a function of x y z, and then you have u x, all these are functions of x y z. Dx, dy, dz, and u is to satisfy equal to sum g x y z on the boundary of this volume V. So, V is a bounded domain in 3 dimension x y z, and its boundary will be a surface delta V like that. So, here we can see that in this case we can proceed in the same manner. We will have phi alpha defined as over V f of x y z, and then u plus alpha delta u, and then u x plus alpha delta u x, u y plus alpha delta u y, and u z plus alpha delta u z dx dy dz, and then phi prime alpha equating at alpha equal to 0, we will have this f u and then delta u plus f u x delta u x plus f u y delta u y plus f u z delta u z dx dy dz, and then shifting these derivatives here, having more general integration by parts formula for 3 dimension, we will have f u minus del x of f u x minus del y of f u y minus del z of f u z, and delta u which is function of x y z, and then dx dy dz, and this is equated to 0, and then having the generalized form of the calculus generalized form of the lemma of the calculus of variations for 3 dimension. We see that here. So, the generalized form of the lemma of the calculus of variation extended for 3 dimension we get f u minus del x of f u x del y of f u y minus del z of f u z equal to. So, that is what we have, and so in general if you have n variables, if I of u is n-fold n times, and you have f of x1, x2, xn and u as a function of x1, x2, xn, and then you have del ux1, ux2 and so on, uxn, dx1, dx2, so on, dx. We get fu minus sigma r equal to 1 to n del xi of f u xi. So, this is we get here for the general case. So, let us put it as 12.5. Now, here in this example we consider R u as triple integral over v u x square plus u y square plus u z square dx dy dz, and u equal to g x y z on the boundary of this volume V. So, this 12.5 in this case for n equal to 3 we get minus 2 u x x minus 2 u y y minus 2 u z z equal to 0, and so or this 3 dimensional Laplacian of u equal to 0 in D in V and u equal to g on delta V. So, that is the Dirichlet problem for 3 dimension. In 3 dimension. Now, if you have mixed kind of or higher order derivatives like this, if R u is of the form that triple integral over V f x y z, or let us do it for 2 dimension and then can be extended. So, that is d and z as a function of x y, z x, z y and z x y, z zxx, zxy and zyy. So, here we have higher order derivatives of the dependent variable appearing, and z equal to g x y on the boundary of D. So, here how do we tackle for the higher order derivatives? We have to take now here the integration by parts for higher order derivatives, which we do. So, integration by parts formulae for higher order derivatives. So, recall that we had this double integral over d n x minus m y dx dy, it was equal to m dx plus n dy. So, if we take n equal to, first if we take n equal to let us say f g and m equal to 0, we see that this f g x plus f x g, that will take on the other side, equal to minus g f x dx dy, and we get here plus, so n is this, so f g dy. So, it is like the derivative of this on g is shifted onto f, and so we get minus sign here. And similarly, if we take n equal to 0 and m equal to f g, then we get y derivative f g y dx dy is minus g f y dx dy plus, rather minus here, because we have this minus sign is to be shifted on to the right, and so you have minus f g dx. So, we take, instead of this we take minus here, minus f g. So, that is what will come here. Now, if we take here n equal to f g x minus f x g and m equal to 0, we get. So, here n is this. So, here we will have double derivatives coming. So, f g x x and then f x g x. So, that again will cancel with f x g x here. So, we will have only terms like this, f g x x dx dy, and we will have here, and in this we will have now f x x g, and with minus sign which will come on the right with plus sign. So, we will have this g f x x over d dx dy, and then here n we have taken like this. So, n dy plus, so this f g x minus f x g here dy. So, this is a second order integration by parts formula, where this x derivative shifted onto f here, and similarly if we take n equal to 0 and m equal to f g y minus f y g, we get f g y y dx dy. This g f y y and then minus over this f g y minus f y g dx. Also if we take now here, since n involves x derivative, so if we take here y derivatives type of this, then we will have mixed kind of a thing. So that is what we will take. So m equal to let us say half of rather n, half of, now here we need to take y once, f g y minus f y g, and m equal to minus half of f g x minus f x g. So we get now over d. So n x will give you f g x y and the terms f x g y and here f y g x, and they will also come from here, they will cancel. So we will have, and half of this plus half of this will make it 1 here. So f g x y dx dy will give you over d g f of x y dx dy, and then plus half of f g y minus f y g dy minus half f g x minus f x g. All these boundary integrals are over C. So these are the higher order integration by parts formulae for this. So these can be used here in this, where you have mixed kind of derivatives x y, and this x x and y y derivatives will be shifted. So here now we consider same way phi alpha like this. So that is double integral over d, and so f of x y and z plus alpha delta z, and then z x plus alpha delta z x, and then z y plus alpha delta z y, and then higher order derivatives z x x plus alpha delta z x x. This is alpha delta z x plus alpha delta z x x and z x y plus alpha delta z x y and z y y plus alpha delta dx dy. So this phi prime alpha at alpha equal to 0 will give us this f z delta z plus f z x delta z x plus f y delta z y plus f z x x delta z x x plus f z y y z x y delta z x y plus f z y y delta z y y dx dy. Now, these first order derivatives will be shifted in the same manner as we have done earlier, and these x derivative, x y derivative and y y derivative of z will be shifted on to f and will give us this. So, here this phi prime alpha equal to 0 will imply, we skip those steps here, just using those integration by parts formula will give us f z del x of z x f z x minus del y of f z y and plus del 2 x x f z x x plus del 2 of x y f z x y plus del 2 of y y of f z y y equal to 0. So, that is the equation we will get in this case. So, we take an example here. So, this is 12.6 and 12.7. So, here I z is z x x square plus z y y square plus 2 z x y square dx dy and z equal to g x y on delta t. And so, here this 12.6. So, 12.6 implies that del 4 of z del x 4 plus 2 del 4 of del x square del y square of z plus del 4 of del y square of z equal to 0, which is known as biharmonic equation. And here z equal to g, this is to be satisfied in D and z equal to g on D. So, the extremals of I are the solutions of let's say this is 12.8, the biharmonic equation. So, now we consider isoparametric problems which were discussed in the first few lectures. So, here we have the following picture. In x y plane there is certain curve C is given of fixed length and it is enclosing the area D here. So, we know that this area of D is this double integral dx dy subject to the condition. So, we have to optimize this or maximize rather So, maximize this such that this length, which is ds s is the small s is the arc length, is fixed. So, given is fixed. So, L is fixed here. So, that is what we have to do here. So, area this is to be maximized subject to the condition that this length L is given fixed number. So, just recall that here we have this double integral over d, this n x minus m y dx dy equal to this m dx plus n dy as the Green's theorem, and if we take n equal to x and m equal to minus y, we get twice double integral d dx dy equal to, so here x dy minus y dx like this. So, area of D is dx dy, and so this is half of this x dy minus y dx. And this arc length S, so here this L is, and integral over C ds, which is square root dx square plus dy square. So, using this, if we parameterize C as x equal to x t, y equal to y t, and t lying between T1 to T2, then we get this area of D as integral over C half of x, which is function of t, then dy by dt minus y t dx by dt into dt. So, in short, we will write it like this: x y dot minus y x dot dt. Here x dot is d by dt of x and y dot is d by dt of y, and this L is then will be integral over C x dot square plus y dot square into d. So, we use the Lagrange's method of Lagrange's method of undetermined parameters. So, we consider I of x, so t x y x dot y dot, and of course, lambda is also there. So, that is T1 to T2 half of x y dot minus y x dot plus lambda square root x dot square plus y dot square and then dt. So, here f is t is the independent variable, x and y are functions of t, and x dot y dot and lambda is also there. So, half of x y dot minus y x dot plus lambda square root x dot square plus y dot square. And so, here we get these equations f x minus d by dt of f of x dot equal to 0 and f y minus d by dt of f y dot equal to 0, because there are two dependent variables x and y. So, these two equations give us half y dot minus d by dt of minus half y plus lambda y dot over square root x dot square plus y dot square equal to 0. Similarly, we get minus half x dot minus d by dt of half x plus lambda x dot over x dot square plus y dot square equal to 0. So, here we get, simplifying this, we get y dot is lambda d by dt of x dot upon square root x dot square plus y dot square equal to 0, and x dot plus lambda d by dt of y dot upon x dot square plus y dot square equal to 0. These can be integrated to get y minus lambda x dot over x dot square plus y dot square equal to C 1 and x plus lambda y dot upon square root x dot square plus y dot square equal to C 2. So, we do not need to integrate it, we can see that y minus C 1 square and x minus C 2 square will give us lambda square. So, we see that we get a circle. So, here obviously, as expected that in this case circle is the one which optimizes this area when the length of the circle is fixed here. And next one we will be considering the geodesics here, and in this case we will have. So, what is the geodesics case? Just recall that we have certain domain D here, and let us say this is the surface here. On this surface we have 2 points A and B, and so here this we need to find the minimum distance between these points A and B, such that these points are moving, these points are there on the surface S. So, such curves are called minimum length on surfaces are called geodesics. So, that we will consider in the next lecture. Thank you very much.